Hello, this is the second video presentation. For this presentation, I'll be explaining a problem having to do with trying to find the power output of a radial turbine when a flow is introduced into it. So for this, you want to be creating some velocity diagrams. Now, in this turbine, something enters at a velocity like such, and it exits here, causing this to turn. It being a turbine because it gets power from the flow of the fluid. So to start off, I want to create a diagram for the inlet velocity. Now the first thing, this absolute velocity, so the velocity of the fluid entering this turbine, hitting this blade, can be written as such. This is V2 at an angle of 25 degrees. Next would be the relative velocity. Now this is the velocity relative to the blade here. So that can be written a bit over from here down as such. Now this is VW, that's how you write it. And now another important aspect of this is the velocity of the blade itself, which can be written up here to create this triangle as U2. Now, U2 is fairly easy to find. It can be found as such, U2 equal omega, which is the angular velocity of this turbine, times the outer radius, which would be the radius at a point like such. Now, this is an RPM, you want to convert it. It is given as 80 RPM, convert it to pi over 60 times the outer radius, get a velocity of 10.05 meters per second. Now, I'll do the same thing for the exit diagram. Exit velocity diagram. Now that'll look something like this. We are given the relative velocity coming down like such to an angle of 30 degrees. Now the blade speed is still going in this direction, meaning absolute velocity would be coming down as such. All right, now solving for the velocity of the blade at the innermost radius, so inside, you get omega R1 this time, 80, convert again. Now this time 0.8 is the radius, get a velocity of 6.7 meters per second. Now it makes sense that these are different because when something's rotating about a point, the further you are from this point, if this rotates 80 times in a minute, it's rotating a further distance than a point, say here. That's why these velocities make sense. Closer in, shorter, smaller speeds, shorter distance, further out, faster speed, further distance, same amount of time. Next, another important aspect of these diagrams here is this little bit here. Now this can be written as the normal velocity. This would be the velocity that is normal to the direction of the speed of the turbine, and that can be calculated out through En equals the mass flow rate of the fluid over the area of the turbine, which then be written out as 2 pi r b, and then such values from the problem. You have 10, 2 pi, 1.2, and now the thickness, and b being the thickness, it is said in the problem statement that the thickness of the blade is 20 centimeters, which would then mean it is 0.2 meters. This then gives us a normal aspect of the velocity of 6.63 meters per second. Of course, the same can be done down here. Come across Vn. Again, normal to the direction of the blade. Vn1 mass flow rate over 2 pi RB, the area, which again was 10. This time 2 pi 0.8, the same 0.2. Percent equaling 9.95 meters per second. Now, one of the most important parts of this, for the power equation, what is needed is the tangential aspect of the velocity, which would equal this whole part here, including this dotted line, can be written as v theta. This is the velocity of the flow, which is tangent to the path of rotation. Now, that can be found, seeing as you have this angle here, 25, can translate up here. You have the tangent of 25. Now this equals, tangent is the opposite over the adjacent, so the opposite being Vn we have 6.63 per second. Now v theta, then when solving for v theta 2, get a value of 14.218 meters per second. Next, for the second part, this one's a little more tricky. You can see that v theta here will only be half of this. Now you can solve that by stating that v theta of 1 is equal to this value here. Sorry, didn't write that out. u1 here minusing Vn tan of 30. This can be shown through this here, this edge here, when you do tan of 30. Again, opposite over adjacent, which would equal this edge here, opposite over adjacent being Vn. Now, this value minus u, you get this right here. That's why you rearrange, solve for this edge, put it there, that becomes your v theta. This then equals u, which we've found to be 6.7 minus 9.95 times the tangent of 30, which then equals a value of 0.955 meters per second. Now, output power. That is given by this equation of rho Q, so rho being the density of the fluid, which in this case is water, Q, volumetric flow rate, of blade speed, and tangential velocity at the inlet minus blade speed and tangential velocity at the exit. This would make sense because since it is a turbine, it's getting force from this, from the flow. So this would have to be bigger because if it wasn't, then it would be something complete. It wouldn't be a turbine. The turbine would have to be producing power into the fluid, which it isn't doing. So when you get these out, this then becomes a value of 999 kilograms per meters 3. Q, volumetric flow rate in this case is 10 meters 3 to the second per second. Sorry. Now this U2 10.05 times tangential minus 6.7 times 0.955. Now when all this is equated out, you get a value of 1,363,559 watts. This can be rewritten, it's much smaller, as 1,363.6 kilowatts. And then this is the power output of this turbine. Thank you.